Unusual plasma waves above Jupiter's north pole, what Juno discovered. Wow! Jupiter just smashed another neat, tidy rule we thought we understood about how plasma behaves in strong magnetic fields, and the details may force scientists to redraw parts of their space weather playbook. Quick recap of the headline. After 9 years of looping around the giant planet, NASA's Juno probe has slipped into a vantage point near Jupiter's north pole where it stumbled upon a brand new kind of plasma wave. At first glance, the oscillations look like the familiar Alfvén and Langmuir waves taught in introductory plasma physics courses, but their frequencies break the standard limits that those textbooks predict. And this is the part most people miss. If Juno can find such a hybrid wave above Jupiter, similar surprises could be hiding around magnetized exoplanets, or even certain stars, waiting for us to notice. But here's where it gets controversial. Textbook theory says that in a dilute, magnetized plasma, electrons collectively wiggle back and forth along magnetic field lines as Langmuir waves at the so-called plasma frequency, while much heavier ions gyrate in circles, setting an upper cutoff, the ion gyro frequency, for Alfvén waves that usually travel perpendicular to the field. Juno's data from the North Polar Magnetosphere refuse to obey that neat division. The Alfvén-type waves ramp up in frequency only until they hit the local plasma frequency, still below the ion gyro frequency, and then never go higher. What's more, the overall spectrum never exceeds the plasma frequency at all. In other words, the classic hierarchy of wave limits appears flipped on its head. To make sense of the puzzle, Robert Lysak and colleagues at the University of Minnesota dug into the relationship between wave number, basically, the inverse of wavelength, and frequency in Jupiter's highly magnetized, low-density environment. Their calculations suggest a smooth transition. As the wave number grows, an Alfvén wave can morph into a Langmuir-like oscillation. Picture it as a musical note that slides from a deep cello rumble to a tinny whistle without ever breaking rhythm. The proposed trigger? Powerful electron beams, ranging from about 1 kilo-electron-volt to a whopping 2 mega-electron-volts, streaming upward along magnetic field lines. Juno first detected such beams over Jupiter's northern auroral zone back in 2016, so the ingredients for the phenomenon were already sitting in plain sight. If the team's interpretation holds, magnetospheric models for Jupiter, Saturn, and any magnetized exoplanet may need an extra term to account for this crossover regime. That could ripple through our understanding of auroral radio emissions, particle acceleration, and even the shielding environments that might protect or strip atmospheres on faraway worlds. And here's a provocative thought: could similar mode switching be hiding in Earth's own auroral zones, overlooked because we never thought to look for it? Or do we need the extreme magnetism and lower densities found near giant planets for the effect to appear? The debate is just getting started. Reference for the deep dive crowd, Robert Lysak et al., New Plasma Regime in Jupiter's Auroral Zones, Physical Review Letters 135, 035201-2025. Now it's your turn. Do you think this hybrid wave challenges the current boundaries of plasma classifications, or is it simply a special case tweaked to known theory? Should mission planners prioritize similar measurements at Saturn, Uranus, or even the Sun's corona? Jump into the conversation and let us know where you stand. Juno detects strange plasma waves over Jupiter's North Pole. In a shocking new revelation that could change everything we know about plasma physics, astronomers have observed an extraordinary type of plasma wave around Jupiter's North Pole. NASA's Juno spacecraft, renowned for its in-depth exploration of the gas giant, has uncovered these peculiar waves, which challenge our traditional understanding of particle behavior within Jupiter's robust magnetic field. This discovery not only raises questions but potentially revolutionizes how we think about plasmas and magnetic fields across the universe. Since commencing its mission in 2016, the Juno spacecraft has been diligently gathering extensive data and images of Jupiter and its various moons, enriching our knowledge of this majestic planet and its surrounding environment. As the mission progressed, Juno's orbit gradually adapted, allowing the team to focus on Jupiter's northern latitudes for the first time, unveiling a unique perspective on the planet's magnetosphere. To put it simply, Jupiter's magnetosphere acts as an invisible shield created by the immense magnetic forces surrounding the planet, extending nearly as far out as Saturn's orbit and stretching approximately 7 million kilometers toward the Sun. This makes it not just the most expansive magnetosphere in our solar system but a prime target for scientific investigation. It's essentially a cosmic laboratory where researchers can study the effects of extreme magnetic forces on plasma and particle interactions. As the Juno team monitored the magnetosphere, they soon realized something was amiss. They detected peculiar plasma behaviors that didn't fit within conventional expectations. This led to an enlightening study led by Robert Lysak from the University of Minnesota, who put forth new theories explaining these atypical wave patterns. The implications of their findings could extend far beyond just understanding Jupiter, offering fascinating insights that might influence how scientists model magnetic fields and related astrophysical occurrences across various celestial bodies. Over the course of nearly 10 years, Juno's orbit has brought it closer to Jupiter's polar regions, where it stumbled upon a low-density area characterized by extremely sparse electron concentrations. In these regions, the magnetic field surged up to 20 Gauss, or 2 metric tons, and revealed a striking anomaly. Plasma frequencies appeared to be significantly lower than the expected ion gyro frequency, which is a fundamental aspect of plasma behavior. Under these unusual conditions, Juno recorded what are known as Alfvén waves. Typically linked with ion movements, these waves seem to adopt characteristics typically belonging to Langmuir waves, which are normally tied to electron activity. This unexpected blending of waveforms has become known as the Alfvén-Langmuir mode, and it raises some eyebrow-raising questions about the nature of plasma physics. Traditionally, plasma physics holds that Langmuir waves oscillate in alignment with magnetic field lines at frequencies that exceed a certain threshold known as the ion gyro frequency. On the other hand, Alfvén waves oscillate at right angles to these lines and are thought to only occur below this threshold. However, Juno's findings suggest that the observed waves have pushed boundaries, showcasing frequencies that, while still below the ion gyro frequency, reached heights typical for plasma frequencies without crossing that critical threshold. What does this mean for our understanding of plasma? It hints at a potential paradigm shift regarding plasma behavior in environments marked by intense magnetization and low electron density. Lysak and his fellow researchers began to delve into the relationship between wave frequency and wave number in Jupiter's magnetosphere, leading them to propose that in such a specialized setting, Alfvén waves could be transitioning into Langmuir waves under specific conditions, a process that could stem from electron beams shooting upward with energies ranging from 1 keV to 2 MeV. Historical observations made by Juno during its encounters with Jupiter's polar regions almost a decade ago reinforced this theory. The implications of this groundbreaking discovery stretch beyond just our understanding of Jupiter. It opens doors to new chapters in plasma physics and may also have significant impacts on our comprehension of magnetospheres around other celestial entities, including distant stars and exoplanets. If similar atmospheric conditions exist elsewhere, the knowledge gained from studying this new hybrid wave mode could greatly enhance our interpretations of astrophysical phenomena across the cosmos. This pivotal research, detailed in a recent publication by R. L. Lysak and colleagues titled New Plasma Regime in Jupiter's Auroral Zones, was made available in Physical Review Letters on July 16, 2025. With such a novel perspective, this research may very well be the key to paving the way for future discoveries in the intricate dance of magnetism and plasma in space. What do you think about these new insights? Could they genuinely reshape our understanding of plasma across the universe, or are they merely an anomaly within the confines of Jupiter? Share your thoughts in the comments below. It would be intriguing to hear where you stand on this fascinating topic. Jupiter's North Pole reveals new plasma wave phenomenon. NASA Juno discovery. What if everything we thought we knew about plasma waves in space was about to be challenged? This is exactly what has happened thanks to NASA's Juno mission, as astronomers have detected a brand new type of plasma wave high above Jupiter's northern pole. It's a discovery that could fundamentally change how we understand not just Jupiter, but potentially the atmospheres and magnetic fields of distant worlds throughout the cosmos. Are we ready to rewrite the textbooks? Let's dive in. Since 2016, NASA's Juno spacecraft has been orbiting Jupiter, peeling back layer after layer of secrets from our solar system's largest planet. Its latest revelation is particularly exciting, and a little controversial. Scientists have recorded an entirely unfamiliar kind of plasma wave in the region around Jupiter's poles. What does this mean for planetary science? You might be surprised. A recently published paper in Physical Review Letters details how astronomers observed a truly peculiar pattern of plasma waves inside Jupiter's magnetosphere. For context, a magnetosphere is like an invisible barrier, a magnetic bubble enveloping a planet and shielding it from harsh radiation pouring in from space. Jupiter's magnetic field is so powerful that it manages to corral extremely different types of plasmas, pulling them into synchronized motion. This generates a unique interplay of electrically charged atoms and particles right at Jupiter's frigid poles. Plasma isn't just an obscure state of matter, it's a powerhouse in the shaping of Jupiter's wild and stormy atmosphere. Scientists believe that this new phenomenon could help clarify not just the violent storms on Jupiter but also how magnetic forces might operate on distant exoplanets circling other stars. Imagine discovering secrets here that could help identify habitable worlds light years away. So, what did the researchers actually analyze? The team, including experts from the University of Minnesota, University of Iowa, and Southwest Research Institute in Texas, studied plasma waves inside Jupiter's intensely magnetized, low-density environment. They spotted a surprising oscillation involving Alfvén waves, which reveal how plasma atoms move, and Langmuir waves, which track how electrons within plasma behave. Usually, because electrons are so much lighter than atoms, the two types of waves operate at totally different frequencies. But Jupiter defied expectations. Inside its magnetosphere, these waves began to oscillate together, unlike anything previously observed in our solar system. John Leif Jorgensen, a planetary scientist from the Technical University of Denmark, who was not involved in the research, remarked that these plasma properties are truly exceptional and completely unprecedented in space science. His reaction? This is the kind of discovery that makes you rethink the building blocks of planetary atmospheres. And here's where it gets especially intriguing: the implications reach far beyond Jupiter. Unlike our own northern lights, powered mostly by eruptions from the Sun, Jupiter's stunning aurora stem from torrents of hyperenergetic particles energized by the planet's massive magnetic field. Some of these particles move at hundreds of times the energy we're used to on Earth. Figuring out how these particles and waves interact can offer major clues for future missions searching for alien life on far-flung exoplanets. Here's a point that's likely to stir debate among astronomers. The study's authors suggest that while such plasma conditions don't exist on our home planet, they may well show up at the poles of other gas giants or on strongly magnetized exoplanets, or even certain stars. Is it possible that planets across the galaxy create auroras and plasma events even more dramatic than Jupiter's? It's a thrilling, but contested, possibility. Scott Bolton, who leads the Juno mission, has called Jupiter the Rosetta Stone of our solar system. Just as the ancient tablet unlocked the secrets of Egyptian hieroglyphs, Jupiter might hold the key to decoding the mysteries of other worlds. It's worth noting that Juno's mission was originally slated to end back in 2017, with engineers planning to crash the craft into Jupiter and meet NASA's strict planetary protection guidelines. However, an evolving flight path meant Juno proved less of a risk to Jupiter's moons than initially thought, letting the mission live on through extended phases. But here's the part most people miss: Juno's journey really is winding down, and by September this year, scientists expect its orbit to decay naturally, eventually drawing the spacecraft into the thick, swirling gases of Jupiter's atmosphere. Still, this isn't a goodbye, not by a long shot. NASA's Europa Clipper is set to reach one of Jupiter's enigmatic moons in 2030, and Juno's treasure trove of data will fuel discoveries for many years. So, what do you think? Can the detection of this new plasma wave rewrite our understanding of how planets and stars work? Could such discoveries pave the way for finding life, or even stranger phenomena, in the universe? Are there other interpretations of these data that deserve more attention? Chime in with your thoughts, questions, or even disagreements below. Let's get the debate started.